Okay. Yeah, I think we're live now, so we can get started. We have a good audience. Okay, welcome everyone. This is our Safari Live seminar number 5, and we have a special guest again this time, Jawad Haj-Yahya from the Huawei Research Center in Zurich. He just started as a principal researcher over there about 2 weeks ago. And before that, he was a part of the Safari research group here in Zurich also for 2 years. Before that, he spent some time in Singapore in multiple places, right, at the university and A-Star as well. And before that, he had a distinguished more than 10-year career at Intel as a processor architect working on power management mechanisms. I think it's 12 to 13 years. Is that correct, Jawad?
Yeah, it's about 13 years, yeah.
yeah. So I'm going reverse chronologically here, and he got his PhD from Haifa University before that. And he's going to talk about some exciting research that he has done in the past couple of years as part of his work in Safari. He's going to talk about power management mechanisms in microprocessors and their security implications. And these works were published in 4 papers that he's going to mention, and you can find all of those papers linked from the YouTube description as well. But I think we'll get started now. Jawad, feel free to share your screen. We can also test that.
Thanks.
And
thanks for the introduction.
I think before you get started, maybe I'll remind people, if people are interested in asking questions on YouTube, feel free to type your questions on the live chat, and we will moderate the questions and ask them at appropriate times, maybe in bulk, for example. Okay, Jawad, the floor is yours. Okay. Thank you.
Thank you, Noor, for the introduction. Could you please give me permission to share screen?
Okay, you should have it now, I think.
Yeah, okay, great. Okay, can you see my screen now?
Yes.
Okay, and so thank you all for joining our Safari Live seminar. So please feel free to ask questions during the seminar at any time. So we are looking forward for good discussions, and I hope that like the discussions will lead to a good high impact future ideas and directions. Yep. So billions of new devices are being deployed every year with new services and features that are driving a high demand for high performance microprocessors, which often have high power consumption. So despite the failure of Dennard scaling, the slowdown of Moore's law, and the high power density of modern processors, power management mechanisms have enabled significant advances in modern microprocessors performance and energy efficiency. So yet current power management architectures also pose serious security implications. This is mainly because functionality rather than security has been the main consideration in designing of power management mechanisms in commodity microprocessors. So in this seminar, we provide a detailed overview of the state-of-the-art power management mechanisms, power delivery networks, and security vulnerabilities of power management mechanisms in modern microprocessors. So first, we present, analyze, and enhance the advanced power management mechanisms of modern microprocessors to improve energy and performance in active and idle power states. And second, we present the design and the trade-offs of modern power delivery networks, evaluate their implications and performance and energy efficiency, and describe new techniques to mitigate PDN inefficiencies. In particular, we will especially introduce the idea of and benefit of hybrid power delivery networks. And third, we present some of the security vulnerabilities that exist in current management mechanisms of modern processors and proposed mitigation techniques. So now I will present our work about techniques for reducing the connected standby energy consumption of mobile devices. So first, I will give high-level overview. So mobile devices operate in connected standby in most of the time. We would like to make this mode more energy efficient. So the problem is that in connected standby mode, mobile devices enter to the deepest runtime idle power state, DRIPS. There are three sources of energy inefficiencies in modern DRIPS. So first, the wake-up timer event is toggled in high leakage process using a high-frequency clock. And the second, several I/O signals are always powered on. And finally, processor context is preserved in high leakage power SRAMs. So our goal is to reduce the power consumption of DRIPS. So we propose optimized DRIPS, which is ODRIPS, which is based on three key ideas. So first, offloading the wake-up timers to low leakage chip, for example, the chipset, with significantly slow clock. And secondly, offload the always-on IOs functionality to power gate all processor IOs. And finally, transfer processor context to a secure memory region inside DRAM. So we implement ODRIPS into Cscale mobile processors, and the ODRIPS reduces the platform average power consumption in connected standby of modern mode by 22%. First, let me give the background of connected standby and DRIPS. So what's actually a connected standby? So mobile devices like phones, tablets, and laptops are idle the majority of the time. So during the idle period, modern mobile devices operate at low power state to increase battery life and remain connected to communication networks for usability, for example, to receive email notification, phone calls, and so on. So the operation mode is called connected standby. Examples like Microsoft Modern Standby or Apple Power Nap. So in the connected standby mode, the system spends most of the time in the deepest runtime idle power state or DRIPS. And during this state, basically the display panel is off and the other devices are sleeping. So in connected standby mode, the system operates in a periodic interval. So basically, we have a periodic interval of active and idle times. In each interval, there is in the active part, the operating system or operating system kernel performs maintenance functions. Most of the time, the system is in idle and enters DRIPS. So according to our estimates, the transition from active to idle takes about 200 microseconds, and the transition from idle to active takes about 300 microseconds. And on average, active residency is about 0.5% and consume about 3 watts, while the idle residency is 99.5% and consumes about 60 milliwatts. So basically, 80% of the connected standby, the platform average power is consumed in DRIPS. So in this figure, we see a processor and chipset. So the chipset is basically a chip that includes several slow IO such as USB, SATA, PCI, audio, and system power management functionalities. And basically, the chipset is fabricated with process that is optimized for low leakage. Then the processor is optimized for high frequency rather than low leakage. So there are three major power consumption sources in trips. So the wake up timer event is toggled in a high leakage process using a high frequency clock. This consumes about 5% of the platform average power. And several IO signals are always powered on. This consumes about 7% of the platform average power. Then processor context is preserved in a high leakage SRAMs, which consumes about 9% of the platform average power. Then also the DRAM, which is in this set in trips in self-refresh, it consumes about 15% of the platform average power. So we target these three inefficiencies in our work. Now I will explain how we tackle these inefficiencies. So again, please interrupt me if you have any question so far. So odd trips consist of three key ideas. So first, offloading wake-up timers to a low leakage chip, for example, the chipset, and significantly slower clock. This saves about 5% of the platform average power, and offloading of always-on IOs functionality to chipset and power gate all processor IOs, which saves 7% of the platform average power. Then we transfer also the processor context to a secure memory region inside DRAM, which saves 9% of the platform average power. Then we have also additional solution for saving the power of the DRAM. I will briefly talk about this later, but also the details are in the paper. Now I will explain how we tackle the first problem. So again, the first problem is that the wake up timer event handling consumes about 5% of the power in trips. So the key idea is basically to offload the wake up timer to a low leakage chip and use a significantly slower clock. So in the baseline architecture, the timer is toggled using a 24 megahertz clock inside the processor PMU. This is done in high leakage process and using a relatively high clock frequency, which is 24 megahertz. So we offload the timer to the chipset, which is fabricated with the low leakage process, and we use other clock, which is the 32 kilohertz clock, to toggle this counter. So let's see how we do that. So first, for this purpose, we add two timers. The first timer is the toggled with 24 megahertz and increased by one each clock cycle. And the second timer is slower, the slow timer, which is actually incremented by step. Step is basically the ratio between the clocks, and step is represent the fixed in the fixed point, and calibrated once every boot. So when the system moves from active to idle, first we transfer the timer from the processor to the fast timer in the chipset. And then the system transfer the fast timer into the slow timer. At this stage, we turn off the fast timer and the 24 megahertz crystal clock. And then basically, this idea saves 5% of the power in trips, because we turn off the fast timer and also the clock crystal from the platform. So now I will describe the second idea. So any questions on the first idea? Okay, so let's move to the second idea.
So,
So
Jawad, I think there is one question online. Well, the first one I think you answered. The question was, can the wake up clock be of slower clock? But that's the idea basically that you proposed. The second question says the wake up in a lot of SOCs is done in a daisy chain fashion, with some logic turned on through header switches to reduce the droop. And the question asks, can this technique be used in addition to the proposed one?
yeah, sure. Here we are talking about wake up time, which is like the overall wake up time as described in the beginning. It's about 200 microseconds, and it's because of the reducing the DIDT effect, and also there is a multiple like steps that are taken, like restoring state and enabling PLLs and so on. So the voltage part, which is for example opening power gates, is normally staggered in order not to consume high DIDT once we are powering up the system.
Yeah, makes sense. I think unless there are other questions from the audience, we can move on.
Okay, sure. Thanks, Onur. So the second problem is that several I/O signals are always on in DRIPs, consuming 7% of the platform average power. So the key idea here is to offload the always-on I/O signals functionality to the chipset and dynamically power gate these I/Os. So two new components appears in the figure. So we have firstly we have the embedded controller, or EC, which is the embedded controller that does multiple functionalities, including system thermal management. And we have also, secondly, we have debug component that connected to the JTAG for both processors and for the processor and the chipset. So the I/O signals that are always on in the baseline architecture are as follows. So we have the 24 megahertz, which is again like was toggling the fast clock, and we have a power management link between the chipset and the processor. We have the thermal reporting from the embedded controller to the PMU of the processor, and we have the debug, which is the JTAG signals that's going to the processor. And so let's see how we can get rid of these signals in ODRIPs and power gate these signals totally. So regarding the 24 megahertz, so we solve this issue because the clock is no longer needed after we offload the timers to the chipset. And the power management links, basically there is no functionality now for them, so no need for power management in ODRIPs. And the thermal reporting, so we actually offload the embedded controller thermal reporting to the chipset using general purpose I/O or GPIO, which is reserved in the chipset. And then the debug signal, so basically the debug is not required, the debug for the processor is not required in ODRIPs. So we use the chipset for debug. And finally, we can add a power gate to the always on I/Os and power gate them once we enter to ODRIPs. So this idea saves about 7% of the original DRIPs power. Now let's move to the third idea. So the problem again is that the leakage power consumption of the save restore SRAMs that saves the processor context in high is high and consuming 9% of the platform average power in DRIPs. So basically the idea is dynamically transfer the processor context from the SRAMs to the DRAM. So let's see how we can do that. So basically two FSMs are implemented in order to flash the processor context from the SRAMs to the DRAM. So basically, the DRAM preserve all its context via using the self-refresh mode, including the processor context. So we move the processor context from the several store SRAMs inside the processor to the basically to the SGX protected memory. So we actually use about 200 kilobytes out of the 128 megabyte of the SGX memory for the safe restore of the processor context during ODRIPs. So both of the SRAMs contexts are flashed using the FSMs into the DRAM area. So this idea saves about 9% of the DRIPS power. So now I will move to the evaluation. So before moving to the evaluation, is there any questions? Okay, so basically, so Intel Skylake for mobile devices includes ODRIPs. We evaluate ODRIPs using real Intel Skylake system, and we use Cscale measurement instruments to measure the data, like the design under test, which is the system. And we can see here in the right side the system and the measurement tools. So we use an in-house power model for sensitivity studies that we conduct in our study. Let's see the results. So basically, the platform average power benefits of each of the three ideas compared to the baseline, which is shown in the first column. The first idea shows 6% platform average power reduction in connected standby. The second idea combines with the first idea, shows 13% average power reduction. And then the third idea shows 9% average power reduction. Then the overall three ideas combined shows 22% average power reduction. So ODRIPS reduces the connected standby platform average power by 22%. So there are other results in the paper. So using non-volatile memories with ODRIPs. So an idea to use phase change memory instead of DRAM in order to save the DRAM power. So this idea reduces the connected standby platform average power by additional 15%. And we use embedded. We have results also for using embedded MRAM inside the instead of basically the on-chip SRAMs, and connected standby average power sensitivity to core frequency in active state and DRAM frequency in active state are also shown in the paper. So let me summarize this paper. So again, like the mobile devices operate in connected standby mode for most of the time. We would like to make this mode more energy efficient. So the problem is that connected standby of mobile devices enters the deepest runtime idle power state trips. There are three sources of energy inefficiencies in modern trips. Wake-up timer events is toggled in a high leakage process using a high frequency clock. Several I/O signals are always powered on, and the processor context is preserved in high leakage power SRAMs. Our goal is to reduce the power consumption of trips, and the mechanisms that we use is optimized trips, which is based on three key ideas. The first one is offload wake-up timers to a low leakage chip, the chipset basically with significantly slower clock. And the second idea is basically to offload the always-on I/O functionality to the chipset. Then the third idea is basically transfer the context of the CPU to the secure memory region inside DRAM. We actually implemented ODRIBs in Intel Skylake mobile processor, and ODRIBs reduces the platform average power consumption in modern connected standby mode by 22%. So actually, we finished this first work. So I will be happy to take additional further questions if you have.
So thanks, Jawad. I think this may be a good time to take some questions related to this work. Maybe I'll start asking some of the questions that are online. There are quite a few interesting questions online, and maybe other people online can think of questions to ask during that time as well. So one question asks, what is the latency impact of doing save, restore to and from DRAM of the context?
Yes, actually, this is a very good question. So like basically, we have the analysis in the paper. Basically, instead, for example, of 200 microsecond, which is the baseline, as far as I remember, it's 200 now, and 15 for the entry, the entry to the state, and the exit is additional about 20 microseconds. So again, it was 300 microseconds. Now it's 320 microseconds, the exit latency of the state. There is no much impact, for example, on the responsiveness of the state. So like the user will start feeling the impact of the latency above one millisecond or even more. So so this state with the additional latency is still useful and very efficient for modern processors.
Mm-hmm. And the detailed analysis in the paper, right?
Yes, exactly.
Okay. A related question to this is considering that the movement of data from DRAM is energy expensive, how does that compare to to keeping the state in local SRAM? Basically, I think the trade-off is SRAM leakage versus dynamic power consumed in data movement between the processor and DRAM.
Yeah, right. Exactly. So like keeping the if you are talking about like saving the state for short time in SRAM, it's it's more energy efficient to keep it in the SRAM. But once we are talking about idleness, as we saw 99% 0.5, like we staying in the drip state. So it's like our analysis show that it's better to offload it to the SRAM, which is to the DRAM, sorry, which is already in self-refresh. Like today's SRAMs are today's DRAMs are being refreshed. All the DRAM also, if the context is there, like is useless. So so what I mean here is that we are not adding additional power to the SRAM to the DRAM. Sorry, once we adding once we moving the context from the on-chip SRAMs to the DRAM.
Yeah, that makes sense. Basically, it's a good trade-off because most of the time is spent in this connected standby mode, and DRAM is already in self-refresh anyway. You're not changing the self-refresh state.
Yes, exactly.
And also the data that you move, the processor context is relatively small, right? You just move it one time and that's it, basically, as opposed to spending a lot of leakage on SRAM to keep that state.
Right, exactly. And the time to move the data is not much time, because like is relatively short, I mean, because like the the bandwidth of the DRAM is very large relative to the data that we are transferring, which is 200 kilobytes. So it's in few microseconds we are doing that.
Sure. So there's another related question, isn't it better to reduce the SRAM supply voltage significantly compared to moving the data to DRAM?
Yeah, this is a good question. Like if you take a look at the paper, we are talking about also like the SRAMs is not just in the operating voltage. They are in the retention voltage. Like if the operating voltage is 0.6 volt, for example, we are talking about 0.4 even, or 4.5. which is the retention voltage. So we already assume that we are reducing the voltage to our retention value.
Makes sense. Basically, the baseline is quite optimized to save leakage in SRAMs. Even then, the idle state is too long, so that you're spending a lot of leakage power if you keep the state in SRAM, right?
Right, exactly.
Okay. One more question is the baseline of Skylake optimized? How about, I think the question is asking, what is the impact of this on ARM cores, for example, which are common in mobile systems?
Yeah, actually, without the details about the processor itself and about the process technology that is used. For example, if we are talking about mobile devices, here, if we are talking about Skylake, which is used for relatively high performance mobile devices, compared to processors that have that's used for smartphones, which have less, which are more optimized for battery life and less performance. So from the beginning, the process technology is optimized for low leakage. So most of the processors that are optimized for high performance, for example, like high-end laptops and high-end even desktops are using two chips, which is one chip for the compute and other chip for chipset or IOs. Like some processor are using IO die for just the IOs, as we discussed in the paper, like IO, the chipset. So this is not common in, for example, in smartphones. But if you are talking about ARM processors for example, for servers or for desktops or for mobile devices like laptops, so then yes, we will have the same issues there.
Okay, I think there's one more question. There are more than one, actually. One question is, what is the absolute value of power saved? I don't know if you have that information, but
yeah, I think we have some data on the paper. I don't remember, but we are talking about 22% average power reduction. If it's significant, if the question is it significant in the in terms of battery life, so yes, it's significant for that benchmark, which is the connected standby benchmark. So like what I can say is that we are talking about average power of a few milliwatts, and we are saving from that few milliwatts to 22%. It's significant for that workload, which is the connected standby workload.
Yeah, and most of the time is spent in connected standby, so it's really almost directly translates to overall power savings, right? During the usage. Yeah,
exactly.
Yeah. I think a couple of questions related to the memory DRAM device. Is it LPDDR4? How big is it? What is the refresh penalty? I assume the self-refresh penalty.
Yeah, the self-refresh penalty is 15% of the average power consumption. And in the paper, we like as mentioned in the additional results in the paper, we are proposing a solution like using a PCM phase change memory instead of DRAM in order to save the 15%. This number is very high. Like self-refresh, like many asking if the self-refresh is basically consuming much in laptop, for example, workloads. So yes, it depends on the workload. So connected standby, the self-refresh power is 15% of this workload. So in order to save it, one solution is using a PCM. But for sure there is other implications for using PCM for other scenarios. But for this scenario, is it's very useful and saves about 15%, additional 15% in top of the 22%. And regarding the DDR itself, as far as I remember, we are talking about LPDDR3, but I'm not sure. Like I need to go back to the paper.
Okay, sounds good. The paper has more details. Basically, if people are interested, they can refer to the configuration that's detailed in the paper.
Yes.
I think the next question is kind of answered because it suggests using Optane devices, for example, and the analysis of that or description of that is in the paper. But of course, there needs to be more analysis for using phase change memory,
right? Right.
Or Optane, right?
Right.
Okay, maybe there are some questions from the audience related to this first part.
Yep. Okay.
I think there are some comments saying that 15% refresh penalty is large, unless the device is large. But I guess it all depends on how much overall power you have, right? If your processor or SoC is quite optimized, then DRAM can spend a lot more fraction of the overall power in your system, right? So it depends, I think. Maybe 15% is large, depending if your processor is spending a lot of power, but it may actually be quite small if your processor is very optimized.
Yeah, right.
Yeah, and this will change, of course, over time, right? As processors and DRAM become optimized in different ways.
Right, exactly.
Yeah.
As I think we are talking about LPDDR3, maybe in LPDDR4 is less power, but like this is the number that we measured directly on the system.
Yeah, so this is based on your direct measurements, right? On a real Skylake system.
Right, exactly.
Yeah, exactly. I think as DRAM devices become more optimized in refresh, that number can get reduced. But of course, processors can become more optimized also over time.
Right. Yeah, which increases the percentage of DRAM refresh. Yeah.
Yeah, exactly.
Yeah.
I think that points to the importance of refresh overall, as we mentioned in the paper as well, and as the audience also mentions. Okay, maybe Giray has some questions. I see him. So.
Hi. So I think you provided an answer to this question partially, but I was curious about the third idea in the reps that you move the context to DRAM. Have you considered HBM-like implementations where you completely eliminate the off-chip communication and see like how much it improves your energy savings?
You mean, sorry, again, regarding HBM? Yeah, sorry.
Yeah, so it's more like, so when you use HBM-like implementation, you don't have the off-chip communication to transfer data from SRAM to DRAM, right?
Right.
So does it affect your energy savings? Does it provide any benefits, or is it completely negligible?
Yeah, I think like using HBM would reduce the overhead of transferring the data. So it makes the state or the RIP state more attractive or more useful for other workload. I mean, like more often, because like the communication, the DDR IO is more consumes more energy than the HBM interface. So like it basically it increases the benefits of ODRIPs.
Okay, that makes sense. Thank you.
Mm-hmm. Okay. So should we continue? No?
Yeah, I think that sounds good. We can come back to this at the end if there are more questions related to it.
Okay. Yeah, so now I will present the next work, which is Cscale, exploiting multi-domain dynamic voltage and frequency scaling for energy-efficient mobile processors. So I will first give high-level overview of the talk. So a modern thermally constrained mobile SoC has three domains: compute, I/O, and memory. The SoC allocates a fixed power budget to these domains unfairly, based on their worst case performance demands, even if they are underutilized. So basically, our goal is to increase the energy efficiency of and performance of mobile SoCs by dynamically orchestrating the distribution of the SoC power budget across the three domains based on their actual performance demand. So the mechanism basically is Cscale, a new multi-domain power management technique that introduces a new DVFS, dynamic voltage and frequency scaling mechanism to distribute the SoC power to each domain based on their its predicted performance demand, and an accurate algorithm to predict domain's performance demand. Then finally, domain-specific techniques to optimize the energy efficiency of each domain at different operating points. So we implement Cscale on the Intel Skylake SoC for mobile devices. Cscale improves the performance of spec CPU 2006 and 3D Mark workloads by 16% and 8.9%, providing large benefits at lower power budgets, and basically reduces the average power consumption of battery life workloads by up to 10.7%. So here is the outline of the talk. So there are three domains in modern thermally constrained mobile SoCs. So we have compute domain, memory, and I/O domain. So several voltage sources exist, and some of them are shared between domains. For example, VDDQ, VIO, vSystem Agent, vCore, and vGraphics. So many components in the SoC normally have their own clock. For example, I/O controllers and engines, I/O interconnect, memory controller, and DDR/IO. Typically, each has an independent clock. So compute domain supports dynamic voltage and frequency scaling. I/O and the memory domains have fixed clock frequency and voltage. So I will now discuss the motivation and goal of our work. So to motivate our work, we evaluate the potential benefit of employing DVFS across the three SoC domains. We carry out an experiment on Intel Broadwell processor under two setups. So baseline setup and multi-domain DVFS setup, or MD-DVFS in short. In the MD-DVFS, we basically reduces the frequency of the DRAM and the I/O interconnect, and we actually reduce the shared voltage and the DDR/IO digital voltage. And we use multiple workload from spec CPU 2006 and 3D Mark, and workload that exercise the big memory bandwidth of DRAM. We make 4 observations of our motivational experiment. I will describe them one by one. So basically, our first observation is about the importance of SOC multi-domain scaling. So we observe that the SOC power budget management algorithm, PPM, assign a fixed power budget to the I/O and the memory domains. The power budget corresponding to the worst case performance demand. When running a 3-spec CPU 2006 workload using baseline and MD-DVFS setups, so we observe that the power of the 3 workloads is reduced by 10%. And the energy of the first workload was reduced by 10%, while the other workloads it was decreased slightly or increased. So basically, the performance of the first workload was slightly degraded, while other workloads experienced a more than 10% performance degradation. So moreover, basically the EDP of the first workload was improved by about 10%, while the other workloads experienced significant degradation in EDP. So the effect of energy efficiency EDP varies widely across workloads. So close look into the bandwidth demand of these workloads. Basically, so the first workload is highly bottlenecked by memory latency, and the DVFS in I/O and memory can reduce power and energy with the minimal performance impact for workloads that not bottlenecked by memory. And our second observation is about the importance of power budget redistribution across domains. So basically, PBM or power budget management algorithm employs a power budget redistribution mechanism between components within a domain. For example, between cores and graphics engines within the compute domain. So current PPMs do not support dynamic power redistribution across different domains. So we evaluate the impact of increasing CPU cores frequency for the MD DVFS setup from 1.2 to 1.3 gigahertz when utilizing the distributed power budget. So we can see that compared to baseline, without MD DVFS, the performance of the first workload was improved by 8%, and the performance of the second and the third workload was degraded by 5 and 10%. So applying DVFS in I/O and memory domains and redistribution that save power budget between domains can improve performance in compute-bound workloads. So our third observation is about memory bandwidth demand in mobile SoC. So basically, multiple components in the I/O and the compute domain have widely varying main memory bandwidth demand across different workloads. So for example, memory bandwidth for demands for some spec workloads, spec CPU 2006 workloads and 3D Mark workloads over time look like this. So several intervals have low bandwidth demands, for example, below 5 gigabytes per second. So in addition, memory bandwidth demand of different SoC engines looks like this. So several SoC engines have a low bandwidth demand for example, below 5 gigabytes per second under some configuration and workloads. So we conclude that typical workloads have modest memory demand, yet the SoC I/O and memory domains are provisioned high. So this makes existing mobile SoC inefficient for typical workloads. So our fourth and final observation is about the importance of optimizing DRAM configuration. So memory reference code, or MRC training, is basically a part of the BIOS code that manages the system memory initialization. So the purpose of MRC training is basically to detect DIMMs and their capabilities, and to configure the configuration registers, CRs, of the memory controller, DDR, IO, and DIMMs. So compared to using optimized MRC values for a given frequency, an optimized MRC values can greatly degrade average power by 22% and the performance of and performance by 10%. Both results were measured in real system, in real Broadwell system using a workload that exercises the big bandwidth of the memory. So we conclude that optimizing the DRAM configuration for each frequency is very important for multi-domain DVFS energy efficiency. So based on our 4 key observations, we conclude that a holistic power management approach is needed to mitigate the power management inefficiencies in current mobile SoCs. So our goal is to provide such an effective multi-domain power management approach by dynamically orchestrating the distribution of the SoC power budget across the 3 domains, by basically based on their actual performance demand. So next, I will explain techniques to achieve our goal. So any questions so far? Okay.
So Jawad, maybe I'll ask one question because I think it's important to point this out. If you go back to this DRAM, unoptimized DRAM configuration, that's a huge difference in terms of average power and performance, right? If you use unoptimized memory reference code configuration values for different frequencies.
Yeah,
I think this is really important to point out. Basically, you need to use optimized memory controller, let's say, configurations for each frequency in DRAM if you want to maximize energy and performance.
Right, exactly. And also the BIOS today, like at least in Intel processors, is doing this optimization. It takes multiple milliseconds in the BIOS runtime, but the benefits, as you can see, like they are huge.
Mm-hmm.
Yeah.
Okay.
Yeah. Okay. Any other questions? Okay. So I will continue. So yeah. Okay. So now I will explain the techniques to achieve our goal. So basically, we propose Cscale. Cscale is a new multi-domain power management technique to improve the energy efficiency of mobile SoCs. Cscale is based on 3 key ideas. So first, a new DVFS mechanisms to distribute the SoC power for each domain based on its predicted performance demand. And secondly, an accurate algorithm to predict each domain's performance demand. Then finally, a domain-specific techniques to optimize the energy efficiency of each domain at different operation points. So Cscale architecture has 3 key components. The first component is a power management flow that is responsible for the DVFS process and reconfiguring the DRAM with the optimized MRC values. And the second component is a demand prediction mechanism that predict the performance demand for each SoC domain. Then finally is a component that a holistic power management algorithm that is responsible for DVFS of the SoC domain to meet basically the system's dynamic performance demand and redistribute the power budget across domains. So now I will explain each of the 3 Cscale components.
Jawad, maybe before you continue further, there's one question. Again, I think this is related to the DRAM.
Okay.
And the question asks, why is there such a big power inefficiency if you don't optimize the MRC values, optimize the memory controller for DRAM? And what are the key parameters that affect things?
Yeah, the parameters. Okay, so the MRC is basically a training process for the DDR IO and the memory controller in order to choose the most optimized latency parameters for the DDR interface. if we are not doing this process, we are using the worst case latency parameters, and this results in high latency on the interface, which results in high energy. Yep.
Okay, sounds good.
Okay. Yeah. Okay. So. Yeah. So the first component is in Cscale. Basically, the power management flow, which is responsible for adjusting the frequencies and voltage for the I/O interconnect and the memory subsystem. So let me go through the steps of the flow. So basically, first, a demand prediction mechanism, which is evaluates every 30 milliseconds, decide on target operation point. And secondly, we adjust the voltage depending on the DVFS direction. Then next, and the next step is basically to block and drain the I/O and the memory domain. Fourth, we place the DRAM into self-refresh. Then we load the optimized MRC values for the new operation point. And next, we adjust the clock frequencies. Then finally, we resume the SOC operation. So the second component is the demand prediction mechanism. So demand prediction mechanism predicts the performance demand using peripheral configuration registers, like CRs, and performance counters. So the peripheral configuration registers indicates the active devices and their configuration. For example, the number of active displays or cameras and frame rates. And we use 4 performance counters with the threshold corresponding to each counter. The performance counters indicates the bandwidth and latency demands of CPU cores, graphics, and the I/O devices. So the last component is the holistic power management algorithm. So Cscale implements a power distribution algorithm in the power management unit firmware. The system moves the I/O and the memory domains to a high or low performance operation point based on the decision of the demand prediction mechanism. The system redistributes the power budget across SOC domains when basically changing the operating point. And for example, when the SOC moves to a low performance operation point, the PMU reduces the power budget for the I/O and the memory domain and increases the power budget for the compute domain, which will increase the performance of the cores or the graphics. So I will next present our evaluation of Cscale. So first, I will present our methodology. So we implement Cscale on real Intel Skylake system. For our baseline measurements, we disable Cscale, and we use SOC with a 4.5 watt thermal design power TDP. We use a National Instrument data acquisition device for power measurements. We evaluate Cscale with 3 classes of workloads. For CPU, we use spec CPU 2006 benchmark. For graphics, we use 3D Mark benchmark. And for battery life, we use web browsing, light gaming, video conferencing, and video playback benchmarks. So comparison point, we actually compare Cscale to 2 most relevant works, which is memscale and Cscale. Basically, memscale applies DVFS only for memory subsystem while Cscale coordinates CPU cores and memory subsystem DVFs. So let me start with showing the results for CPU workloads. So Cscale improves improves real system performance by 9.2% on average. And Cscale provides 5.4 and 2.4 times the performance improvement of Memscale and Cscale. So this is because Cscale is holistic, taking into account all SOC domains. And unlike the other mechanisms, Cscale optimizes the DRAM interface. The performance benefits of Cscale correlate with the performance scalability of the running workloads with the CPU frequency. So we conclude that Cscale significantly improves the CPU core performance by holistically applying DVFS to SOC domains and redistributing the power budgets. Now let us see the results for the graphics workloads. So Cscale improves real system performance between 6.7 and 8.9% because Cscale boosts the graphics engine's frequency by redistributing the power budget across the 3 domains. And Cscale provides approximately 5 times the performance improvement of Memscale and Cscale. Memscale and Cscale have similar performance improvements because their average power savings are identical. This is because graphics workloads in graphics workloads, CPU cores run at the lowest possible frequency. Therefore, Cscale cannot further scale down the CPU frequency. So we conclude that Cscale significantly improves the graphics performance using the saved power budget from I/O and memory domains. Now I'll present the results for battery life workloads. So battery life workloads normally have a fixed performance demand. Cscale reduces the average power by between 6.4 to 10.7 and on real processor and workloads. And Cscale provides approximately 5 times higher power reduction compared to Memscale and Cscale. So Memscale and Cscale have similar average power reduction because this is because in the battery life workloads the CPU cores run at the lowest possible frequency, and therefore Cscale cannot further scale down CPU frequency. So we conclude that Cscale significantly reduces the SOC average power consumption. So we have more results in the paper. For example, Cscale performance and average power consumption sensitivity to system TDP, thermal design point. And so Cscale performance benefits increases as TDP decreases, and Cscale improves energy consumption across the entire TDP range. We also have results for different DRAM frequencies and types. Let me quickly conclude my talk. So again, Cscale is the first work to enable coordinated and highly efficient DVFS across all SOC domains to increase energy efficiency. And Cscale optimizes and efficiently redistributed the total power budget across all SOC domains based on the performance demand of each domain. We implement Cscale on Intel Skylake SoC for mobile devices. Cscale improves the performance of real CPU and graphics workloads by up to 16% and 8.9% respectively for 4.5 watt TDP. Cscale reduces the average power consumption of battery life workloads by up to 10.7% across all TDPs of the Scale system. So we conclude that Cscale is an effective approach to balance power consumption and performance demand across all SOC domains. So we completed the second basically work. I will be happy to take any further questions.
So thanks, Jawad. Maybe I'll aggregate some questions and others can ask afterwards. I think this is definitely a good work in the right direction. It's good to holistically manage power across the entire SOC as opposed to having components that do their own thing and do not coordinate with each other, right? I think we'll probably see more and more of such mechanisms going into the future for performance as well. In my opinion, we need to be more holistic in such management. There's one question that's, I think, interesting. You have a demand prediction mechanism, right, in Cscale. And this question is asking, did you try any machine learning based demand prediction algorithms compared to heuristics that you're using?
Yeah, and in our work, we didn't use a machine learning prediction. I saw follow-up works that try to do this, and definitely they can improve our algorithms on top of the results that we have.
Mm-hmm. Yeah, makes sense. I think more sophisticated algorithms will certainly provide better improvements based on the same general framework.
Yep.
There's another question related to the Cscale. Are the other baselines used for comparisons from Safari, or are they other independent works?
Again, what do you mean? The baseline? Our baseline is just disabling, like in the methodology I'm explaining this, disabling the feature itself and see like without Cscale, what's the system, how the system is behaving.
Yeah, I think can you go to the methodology slide? I think it'll become more clear.
Yeah,
I think the question is asking the Cscale and the memscale baselines.
Ah, okay.
And maybe I'll. Yeah, go ahead.
Yeah, I mean the Cscale and the Cscale, sorry, Cscale and the memscale are not measured. We didn't implement them. So basically, we estimated them based on the data that we have. It's like power modeling, power and performance modeling. Yeah, makes sense. I think, yeah, these are not works from Safari. Memscale and Cscale are done by others, and Jawad is correct in mentioning how we implemented them. But the memscale idea is concurrent work with one Safari and Intel work in the past. This is memdvfs that we published in ICAC in 2011, concurrently essentially. And in that work, we saw similar results to what Jawad presented. Basically, we saw about the idea is dynamic voltage and frequency scaling of the memory devices, only DRAM basically. And we saw about 3% energy reduction by doing this. And I think your results are around the same ballpark, let's say, if not exactly that way. Okay, I think there's one maybe a question that's not easy to answer with the methodologies that we have, but what is the ideal performance improvement possible, and how much of that is achieved by Cscale? It's really we didn't quantify the like absolute optimum here, but I think there is options to improve based on the algorithm improvements. And I saw that in other papers that they like follow-up papers of our work, and they improve the performance in additional few percentage by applying a more optimized like algorithm. So like here we didn't check the optimized I mean the optimal solution because sometimes the optimal solution is also depends on the latency to run to like move between one state to the other state. And if we want the optimal solution, we need sometimes to assume like 0 microsecond transition between one state to other state, which is not practical. So we in this work, we actually explore a practical solution for existing system. By the way, like the transition time between one state to the other is typical in all the current system that I mean the current processors, not just from Intel, from other vendors.
Yeah, and I will also add that ideal is very difficult to get, I think,
Right.
in general, because you're optimizing multiple different parts of the system, and even simulating that is difficult, I think. I think one last question from YouTube related to going back to the memory reference code, digging a bit deeper, which timing parameters are configured using memory reference code, MRC?
Yeah, there is multiple details on that, like much more details on that on the paper with the names of the configuration registers. But basically, this is configuration registers inside that are responsible for the transition time on the DDR IO itself and on the like in the side of the memory controller and on the side of the DRAM device. So there are multiple registers there that need to be optimized. Again, this process is not new. It's called MRC. It's happened in the BIOS time, but the special thing is that we applying this for the different frequencies. So what we did in this work is having SRAM that saves different configurations for the different working points that we are moving between them dynamically, and the algorithm or the mechanism basically pulls the correct data from these SRAMs dynamically. We fill these SRAM values in the boot time. So in the boot time, we switch between all the possible frequencies of the system of the memory basically, and we figure out using the MRC algorithm which parameters are more optimized for that, or the most optimized for that work point.
Okay, sounds good. If there are other questions, I think people can ask now. I don't have anything else at this point.
Hi there, Jawad. I have a question that's related to the DRAM. So
Yep.
I'm thinking about LPDDR5, which is now coming into production and has some features for both frequency and voltage scaling, just to manage the power consumption of the low power states and things like that. So I'm wondering how this interacts with Cscale, and does it just work with Cscale, or is this even better for Cscale's power management methodology, or does something need to be changed?
Yeah, so regarding LPDDR5, as far as I know, like all the DRAMs, including the LPDDR5, are their voltage, the voltage which is for the array, it cannot be adjusted dynamically. This is because it requires multiple optimization for the DRAM for arrays and the analog parts in different voltage. So our assumption in our paper and the paper that we compared ourselves to them, our paper to them. So they are not changing the DRAM voltage itself. We are talking here about only the VDDQ, which is the voltage for the we are adjusting only the voltage for the memory controller, and while keeping the other voltages are the same for across all the frequencies. So as far as I know, like I took a look at DDR5 also, the frequency there, the voltage there is should not be adjusted once you change a frequency. The obvious change in the LPDDR5 is that there is integrated voltage regulator inside the DIMMs, which helps increasing, for example, the yield of the DRAM. But it also has some cons, for example, if each DRAM now need to have its own integrated voltage regulator, and there is no specification. There's no clear specification on the efficiency for that LPDD, for that integrated voltage regulator. So, like DRAM vendors can choose an efficient solution, while like it will affect at the end the total efficiency of the system. So again, like to keep it short, like LPDDR5 and the other DRAMs do not assume that we can change the voltage once we change the frequencies, and also our work is not assuming this.
Okay, thanks for clarifying.
Yeah. Okay, any other questions? Okay, so let's move to the next work. So the next work is FlexWatts. So FlexWatts is a power and a workload-aware hybrid power delivery network for energy-efficient microprocessors. So in recent years, basically there is a hot debate in industry and academia on power delivery networks. PDN issues are becoming even worse as process technology scales down. So first, I will give high-level overview of the talk. So client processors typically use one of three commonly used power delivery networks architectures: motherboard voltage regulators, integrated voltage regulators, and low drop output voltage regulators. The energy efficiency of each of these PDNs varies with the processor power and workload characteristics. Our goal in this work is to provide highly energy efficient and high performance PDN architecture by leveraging the advantage of each one of the three PDN architectures across processors' wide range of power consumption and workload. So to this end, we propose FlexWatts, a new hybrid and adaptive PDN for client processors that introduces three mechanisms. So first, a new hybrid voltage regulator that are allocated for processor domains with a wide power consumption range that dynamically switches between two modes, IVR mode and LDO mode. And secondly, a static allocation of off-chip VRs with a high that have high energy efficiency for low and narrow power range for the rest of the domains. And finally, a novel prediction algorithm that switches the hybrid PDN to the mode that is the most beneficial based on the processor power and workload characteristics. We evaluate FlexWatts using a new architectural PDN spot. PDN model, PDN spot. FlexWatts improve the average power, the average performance of spec CPU 2006 and 3D Mark workloads by 22% and 25% respectively for 4-watt thermal design power system. And FlexWatts reduces the average power consumption for video playback workloads by 11% across all TDPs. So there is here is the outline of that talk. So I will begin with a brief overview of client PDN architectures. So there, the power delivery network is the electrical system that provides supply voltage to the processor domains. A PDN consists of a power supply, voltage regulator, network of interconnects, decoupling capacitors, and power gates. There are three different commonly used PDNs. These PDNs normally use switching VRs and or low drop output VRs. So an SVR can be placed into the motherboard, which is called MPVR, or integrated into the chip, which is called IVR. So the PDN performs differently based on the processor power and workload characteristics. Motherboard VRs, for example, and LDO PDNs, motherboard MPVR and LDO PDNs are more energy efficient at low thermal design power and light workloads compared to IVR. IVR is more energy efficient at high TDP and heavy workloads than LDO and MPVR. MPVR is more energy efficient than LDO in graphics workloads. So we conclude that a single PDN architecture cannot provide high energy efficiency across a wide power consumption range and wide variety of workloads. So I will now discuss the motivation and goal of our work. So we evaluate the potential benefits of the three PDNs, IVR, MPVR, and LDO across different TDP, application ratio, and workloads. Application ratio is basically a switching rate of a component for a workload when compared to the highest possible power, which is power virus. So we use our validated model PDN spot to evaluate the efficiency of the three PDNs. We use metrics. We use the metric end-to-end power conversion efficiency. So basically, end-to-end efficiency of a PDN is the ratio between the total output power consumption to the input power consumption of the PDN, as you can see here in the image. So we use multiple workloads. We use multiple workload traces from SPEC CPU 2006, 3D Mark, and video playback workloads. So our observation about the TDP, our first observation is about the TDP effect on PDN efficiency. So when executing CPU and graphics intensive workloads with different application ratios, so we observe that IVR PDN has a lower end-to-end efficiency at 4 watt, and we observe that and for what TDP compared to motherboard VR and LDO PDNs. And we observe that the IVR PDN has a higher end-to-end efficiency at the 50 watt TDP compared to motherboard VR and the LDO PDNs. The end-to-end efficiency crossover point at which the IVR end-to-end efficiency becomes higher than the MPVR or LDO end-to-end efficiency exists at some TDP between 4 watt and 50 watt. So we conclude that a TDP affects the end-to-end efficiency of PDN, and at low TDP, the MPVR and the LDO PDNs are more efficient. At high TDP, the IVR PDN is more efficient. Our second observation is about the workload effect on PDN's efficiency. So workload application ratio and the workload type affects PDN end-to-end efficiency. The end-to-end efficiencies of MPVR and LDO PDNs increases with application ratio due to load line effect. Different workload types has different end-to-end efficiency curves. So, for example, the LDO end-to-end efficiency is higher than MPVR end-to-end efficiency for CPU-intensive workloads, but lower than MPVR end-to-end efficiency for graphics workloads. LDO inefficiency is more dominant in graphics workloads due to the high voltage difference between the cores and the graphics domains. So we conclude that application ratio and the workload type have significant effect on each PDN's end-to-end efficiency. MPVR and LDO PDNs have lower end-to-end efficiency with low application ratio. LDO PDN has a low end-to-end efficiency on graphics workloads. And our last observation is about power state effect on PDN's efficiency. So the end-to-end efficiency of IVR is lower than that of MPVR and LDO PDN for computationally light workloads and low power states across all TDPs. So a video playback workload spends 10% and 90% of its execution time in light workload and a low power state, respectively. MPVR and LDO have 12% and 11% lower average power consumption, respectively, than the IVR PDN due to high end-to-end energy efficiency for MPVR and LDO PDNs, as we can see here in the picture. So we conclude that IVR PDN is energy inefficient for computationally light workloads. Basically, this negatively impacts the energy efficiency and battery life of the system. So based on our three key observations, we conclude that there is no single PDN for modern client processors that provide a high end efficiency across all TDPs, workload types, and application ratios. So our goal is to provide a PDN architecture that provides high energy efficiency across the wide range of power consumption and a variety of workloads. And now I will explain the technique to achieve this goal. So we propose FlexWatts. FlexWatts is a hybrid adaptive PDN that provides high end-to-end efficiency for the wide power consumption range and workload density diversity of client processors. FlexWatts is based on three key ideas. First, new hybrid voltage regulators that are allocated for processor domains with wide power consumption range that dynamically switch between two modes, IVR mode and LDO mode, to maintain basically high energy efficiency across the wide range. And secondly, a static allocation of off-chip VRs, which have a high energy efficiency for low and narrow power range for the rest of the domains. And finally, an novel prediction algorithm that switches a hybrid PDN to the mode that is the most beneficial based on processor power and workload characteristics. So FlexWatts has three key components. a hybrid adaptive PDN that includes hybrid VRs and off-chip VRs, a novel noise-free mode switching that is transition the hybrid PDN between two modes, IVR mode and LDO mode. And finally, a new mode prediction algorithm that automatically determines which PDN mode would be the most beneficial based on system and workload characteristics. So now I will talk about each component in more details. So the first component is hybrid adaptive PDN. So basically, FlexWatt's PDN consists of two components. An off-chip VR allocates to each system domain with a low and narrow power consumption range, and a hybrid VR which is allocated to system domains with a wide power consumption range. The hybrid PDN can dynamically switch between two modes, IVR mode and LDO mode, based on the expected energy end-to-end efficiency benefits of each mode for the current workload and power consumption. The hybrid PDN shares multiple die, package, and board resources to reduce cost and area. Okay, so the second component is a voltage noise-free mode switching mechanism. FlexWatt performs mode switching using three-step while the compute domain are idle to prevent any voltage noise. So first, we place the processor in an idle power state for a short period of time. Secondly, we configure the hybrid PDN and update the on-chip and the off-chip levels finally, we exit the idle power state and resume the processor with the new PDN mode. The final component is the runtime mode prediction algorithm. A new runtime mode prediction algorithm predicts which PDN mode among the two modes, IVR and LDO mode, provides the best end-to-end power conversion efficiency. So end-to-end efficiency is function of application ratio and the workload type. For example, single thread, multi-thread, and graphics, and the TDP and the power state of the system. We store two sets of end-to-end efficiency curves inside the power management unit firmware. One for the IVR PDN and the other set for the LDO PDN. So the PMU firmware estimates each of the input parameters at runtime. So I will next present our evaluation of FlexWatt. So first, I will present our methodology. So we evaluate PDN. We evaluate the PDNs using our new open source PDN spot model, and we evaluate FlexWatt with the three classes of workloads. For CPU, we use spec CPU 2006 benchmarks. For graphics, we use 3D mark benchmarks, and for battery life, we use web browsing, live gaming, video conferencing, and video playback benchmarks. So we compare FlexWatt to the three commonly used PDNs, IVR, MBVR, and LDO PDNs of client processors. So let me start with showing the results for the CPU workloads. So at TDPs lower than 18 watts, FlexWatt provides up to 22% higher performance and I have higher performance over the IVR PDN by operating mainly at LDO mode. And at TDP is higher than 18 watts. FlexWatts provides up to 7% and 4% higher performance over MPVR and LDO PDNs by operating at IVR mode. FlexWatts significantly improves the CPU performance compared to IVR at low TDPs by operating in LDO mode. FlexWatts provides high CPU performance compared to MPVR and LDO at high TDPs by operating in IVR mode. Now let's see the results for the graphics workloads. So at TDPs lower than 25 watts, FlexWatts provides up to 25% higher performance over the IVR PDN by operating mainly at LDO mode. At TDPs higher than 25 watts, FlexWatts provide up to 3% and 6% higher performance over MPVR and LDO PDNs by operating mainly at IVR mode. At TDPs lower than 5 watts, FlexWatts provides slightly worse, up to 2% than basically MPVR and LDO PDNs due to the high load line of FlexWatts, the large difference in operating voltage across the cores and LSC and graphics domains. So we conclude that FlexWatts significantly improves the graphics performance compared to IVR and at low TDPs by operating in LDO mode. FlexWatts provides high graphics performance compared to MPVR LDO at high TDPs by operating at IVR mode. Now I'll present the results for battery life. So battery life workloads have fixed performance requirements. They consume the same power nearly the same power at all TDPs. So FlexWatts reduces the average power consumption between 8% and 11% on battery life workloads compared to IVR PDN. FlexWatts consumes up to 1% more power consumption, more power than basically MPVR PDN. So we conclude that FlexWatts almost as energy efficient as MPVR and LDO, and up to 11% more energy efficient than IVR mode for battery life workloads. So we have more results in the paper. For example, FlexWatts board area and the bill of materials BOM cost compared to other PDNs. And basically, FlexWatts have significantly lower BOM cost. FlexWatts have a comparable BOM cost to and board area to IVR, and FlexWatts have significantly lower BOM cost and board area compared to MPVR and LDO. And so comparison to PDNs used in Intel Skylake X processors that combine IVR and MPVR PDNs. So Intel Skylake PDN, Intel Skylake X PDN provides higher performance and lower energy consumption than IVR PDN. But the FlexWatts provides significantly higher performance and lower energy consumption than Intel's Skylake X PDN. So let me quickly conclude my talk. So basically, client processors typically have one of three commonly used PDNs: MPVR, LDO, MPVR, IVR, LDO. The energy efficiency of each of the PDNs varies with processor power and workload characteristics. Our goal is to provide high energy efficiency and high-performance PDN architecture by leveraging the advantage of each one of the three PDNs architecture across the processor wide range of power consumption and workloads. So FlexWatt's a new hybrid adaptive PDN for client processor that introduces new hybrid voltage regulators that are allocated for processor domains with a wide power consumption range, and that dynamically switches between two modes, IVR mode and LDO mode, and static allocation of off-chip VRs with which have high energy efficiency for low and narrow power range for the rest of the domains. A novel prediction algorithm that switches the hybrid PDN to the mode that is most beneficial for based on the processor power and workload characteristics. So we actually evaluate FlexWatt's using our new architectural power delivery model, and FlexWatt improves the average power consumption of spec CP 2006 and 3D Mark workloads by 22 and 25% respectively for 4-watt TDP, and it reduces the average power consumption of video playback by 11% across all TDPs. So we actually completed the third work. So I'll be happy to take any questions.
Hey, Jawad. So we have one question in YouTube chat. So the question is, how do you estimate the overall performance loss due to switching across IVR and LDO modes?
Yeah, so we estimated that based on our model. There is a overhead of switching between the two modes. The overhead is about 100, around 100 microseconds. So our model take that into account. So please note that in some states, for example, like once we are talking about like 4-watt TDP, so like almost there is no need to switch between one mode to the other, and the same is correct for 50 watts. So that, I mean, the edges are of the TDP. Either you are allocated for a IVR mode or you are working on LDO mode. The overhead is mainly in the TDPs that are in the middle, like between 18 watt and 25 watt, and we take that into account in our model.
Yeah, great. I think that answers the question. So I'll ask another question. So to me, it seems like this prediction model is quite important for this work, right? So
yep.
How simple or how complicated kind of prediction algorithm are we implementing there? Could you elaborate a little bit more on this to give some insights, basically?
Yeah, we actually here we choose a simple solution, like we having a table that have a curve, like the curves that we saw in the. Let me go back to the one of the drawings. Yeah, so the curves that we have, for example, for some workloads, I mean, the curve that shows the application ratio with the end-to-end efficiency. So we simply save them as tables inside the firmware. There is option also to have a more like more complicated and more accurate estimations, like by having machine learning algorithms. But here we choose a simple solution that shows significant improvements over baseline, and the additional benefits can be applied again by having a more accurate prediction algorithm.
Yeah, makes sense.
Mm-hmm.
So I'll have another high-level question, actually not particular for FlexWatt, but for all three works that are focused on energy efficiency. So, you know, in the industry or for the end users, these ARM-based processors have been quite popular because of the perception that they have a good energy efficiency. So, in your recent works, particularly these works that you presented, you apparently reduced the energy consumption significantly. And yeah, considering all these, how do you see the difference between Intel-based or ARM-based processors or some other alternatives as well? And what do you think as like the next part of the processor design that we should focus on to further reduce the energy consumption? If this is not like very private.
Yeah, thanks, Dira. I think it's a very important question. Like some people think that, for example, ARM based SoCs are more energy efficient because they are using RISC or versus CISC that is used for Intel, which I don't believe so. Like I think that it's based on history, because like mostly ARM-based SoCs were focused on the low TDP or the portable devices like dmartphones, and while Intel and AMD were focusing on the high performance part, like desktops and then laptops and high end laptops and also servers. So the energy efficiency features like what I presented here and many more were deployed first in ARM processors because the battery life and the energy efficiency was very important to these devices. And we like in recent year we are seeing ARM and we are seeing Intel and AMD processors are being more and more energy efficient. So I think there is no magic here. Like the same features that applies for ARM can be also ported or deployed in Intel and ARM and AMD processors, and this is happening. And the gap is being closed. I mean, it will be fully closed in the near future. So I don't see essential limitation that is there like in an ARM based SoCs versus Intel and AMD. Also there we also see some solution like hybrid heterogeneous cores, for example. I see that in Intel the recent processors. I think also AMD are playing that in the future, but this is for increasing the energy efficiency, which is already many years exist in ARM-based processors like the big and the little processors. Cores. So again, like these features can be applied to the entire SoC from all vendors.
Yeah, I see. That's very promising. It's very nice to hear that. I think we don't have further questions, so maybe you can go on with the fourth paper then.
Yeah, sure. Thanks. Yeah, okay. So we finished this paper. So let's move on to power management vulnerabilities. So basically, there are several attacks that exploit different power management vulnerabilities of modern processors. For example, some of the work that were recently published, like catching the flow, which is creates two attacks that significantly degrade the power efficiency by increasing hardware, by inserting a hardware Trojan in the power management unit in the PMU. Other work that has another attack, which is the clock screw, which proposes an attack that infers secret keys by enforcing autonomous frequencies and voltage in the DVFS and inducing timing errors. Other work is DVFS covert. Basically, it creates a covert channel between a Trojan and a spy process by modulating the process operating frequency with the help of power governor of the operating system to stealthily exfiltrate the data of the secret data. And the additional work is Cscale basically creates a covert channel between independent FPGA boards in a data center by using the power supply unit without physical access to the board. So I will present a part of our ESCA 2021 work related to this topic and compare it to recent work. So now, like our next paper will be iChannels exploiting current management mechanisms to create covert channel in modern processors. So I will first give high-level overview of the talk. So current management mechanisms throttle instruction execution and adjust voltage and frequency to accommodate power-hungry instructions, PHIs. These mechanisms make compromise a system's confidentiality guarantees. So our goal is basically first to understand the throttling side effect of current management mechanisms, and secondly, to build a high capacity covert channel between otherwise isolated execution contexts. And finally, to practically and effectively mitigate each covert channel. We characterize the variable execution time and the frequency change due to running PHIs. We propose 5 different levels of, we observe 5 different levels of throttling in real systems. We propose iChannels, a new covert channel that exploits side effects of current management mechanisms on the same hardware thread across co-located simultaneous multi-thread threads and across different physical cores. On 3 generations of Intel processors, iChannels provide a channel capacity of 2 times that of PHI's variable latency-based covert channel and 24 times that of power management-based covert channels. So here is the outline of the talk today. I will begin with a brief overview of client processor architecture. In many recent processors, CPU cores share the same voltage regulator and clock domain. Central power management unit controls the voltage regulators using off-chip serial voltage identification interface, the clock phase loop using on-chip interface, and each CPU core has a power gate for the entire core. Each SMID unit, IMD unit has a separate power gate. So the relationship between load voltage, VCC load, supply voltage, VCC, and current ICC under a given system impedance R load line is VCC load equal VCC minus ICC times R load line. So as shown in the following figure, the power management unit adds a voltage guard band to VCC to a level that keeps the VCC load within limits above the minimum functional voltage VCC mean under the most intensive workload power virus with a current ICC virus. and below the maximum operational voltage VCC max under the lightest load leakage with current I leakage. For loads with current lower than ICC, basically the voltage drop is smaller than when running a power virus, resulting in a high load voltage than necessary, leading to a power loss that increases quarterly with the voltage level. So I will now discuss the motivation and goal of our work. So prior works have multiple limitations. NetSpectre exploit variable execution times of PHIs to create a covert channel. NetSpectre has three limitations. So first, it established only between two execution contexts in the same hardware thread. And secondly, it uses only single level throttling side effects, which is throttled or unthrottled. And finally, it does not identify the true source of throttling. NetSpectre hypothesized that the throttling is due to power gating of the PHI execution unit. And TurboCC exploit the core frequency throttling when executing PHIs to create cross-core covert channel. TurboCC has two limitations. So first, it focuses only on the slow in milliseconds, basically side effects of frequency throttling that happens when executing PHIs at only turbo frequencies. And basically, it does not uncover the real reason beyond the vulnerability. So the work hypothesized that the frequency throttling is due to thermal management. So recent works propose limited covert channel and the use inaccurate observations. So our goal in this work is to first experimentally understand the throttling side effect of current management mechanisms in modern processors to gain several deep insights into how these mechanisms can be abused by attackers. And secondly, build high capacity covert channels, I channels, between otherwise isolated execution context located on the same hardware thread across SMT threads and across the different physical cores. And finally, practically and effectively mitigate covert channels caused by current management mechanisms. Now I'll present the throttling characterization. So we experimentally study three modern Intel processors, Haswell, Coffee Lake, and Cannon Lake. We measure voltage and current using data acquisition card and IDAC. So here is the picture of the system. So we study the impact of power-hungry instructions on the CPU core supply voltage VCC. We track the VCC change during an experiment on two cores Coffee Lake system executing code that includes AVX2 phases. So VCC increases once the CPU core begins executing AVX instructions, and the more cores executing AVX instructions, the higher the VCC. The voltage emergency avoidance mechanisms prevent the core's voltage from dropping below the minimum operational voltage limit when executing PHIs. We use the following system for the next experiment. So we use a single core Coffee Lake desktop CPU operating at turbo frequency 4.9 gigahertz and 4.8 gigahertz. and two core Cannon Lake mobile CPU operating at turbo frequencies 3.1 and 2.2 gigahertz. We execute a non-AVX and AVX2 workloads while measuring current and voltage. The bars with the green border are projected. Here are the VCC max and ICC max limits of the system. So for both desktop frequencies, ICC is below ICC max limit. And VCC will exceed the voltage limit VCC max when executing AVX code at a frequency of 4.9 gigahertz. For both mobile frequencies, the voltage VCC is below the VCC limit, which is VCC max. ICC will exceed the current limit ICC max when executing AVX code at a frequency of 3.1 gigahertz. So contradictory to the state-of-the-art work hypothesis, the core frequency reduction that directly follows the execution of PHIs at turbo frequencies is not due to thermal management. It's due to maximum instantaneous current limit, ICC max, and maximum voltage limit, VCC max protection mechanisms. So we study we study the time it takes to open AVX power gate for Coffee Lake by comparing it to Haswell system, which does not have AVX power gate. So when running AVX instructions in a loop consisting of 300 AVX instructions that use registers, basically the first iteration of the loop running on Coffee Lake is more than 8 nanoseconds. It's more than 8 nanoseconds longer than that of the 2 iterations. And for Haswell processors, all iterations have nearly the same latency. So so the following graph shows AVX throttling with the zoom into power gating in the right side. So the AVX power gating feature has approximately between 8 and 15 nanoseconds of wake-up latency, about 1% of the total throttling time when executing PHIs, which is greater than 10 microseconds. So contradictory to the state-of-the-art work hypothesis, power gating AVX instruction unit accounts only for 0.1% of the total throttling time observed when running PHIs. So the majority of the throttling time is due to voltage transitions. So we execute 7 instruction types in a loop, followed by 5 12-bit heavy loop. Heavy loop instructions are instructions that require floating point unit or any multiplications. So the throttling period of the 512 heavy loop increases when the computational intensity of the instructions executed in the preceding loop decreases. The lower the instructions computational intensity in the preceding loop, the lower the applied voltage guardband to these instructions. Hence, the 512 heavy loop requires more time to increase the voltage to the required level. So we observe at least 5 throttling levels, level 1 to level 5, corresponding to the computational intensity of instruction type. So current management mechanisms result in a multi-throttling level period depending on the computational intensity of the PHIs. And we study the source of throttling and its microarchitecture impact. We track the number of micro-ops or UOPs that the core pipeline delivers from the front end to the back end during throttled and unthrottled AVX loops. So the front end the front end does not deliver any UOPs in approximately 3/4 of the core cycles, even though the backend is not stalled. The core uses a throttling mechanism that limits the number of UOPs delivered from the front end to the back end during a certain time window. We found that this throttling mechanism affects both threads in SMT. So contradictory to the state-of-the-art hypothesis, the 4x core IPC reduction that directly follows the execution of PHIs is not due to reduced core clock frequency by 4x, but it's rather because the core blocks the front end to the back end UOP delivery during 75% of the time. So these throttling mechanisms affects both threads on SMT cores. Now I will explain the covert channels of I-channels. So the threat model consists of two malicious user-level attackers, attacker application sender and receiver, which cannot communicate through overt channel. We build the 3 high throughput covert channels between a sender and receiver that exploit the throttling side effects of current management mechanisms on the same hardware thread across SMT threads and across cores. Each covert channel sends 2 bits from sender to receiver in every transaction. Every covert channel should wait for a reset time before actually sending additional transaction. And we demonstrate the covert channels in Intel Cannon Lake real system. So now I will talk about each of the covert channels in more details. The first covert channel is ICC thread covert established on the same hardware thread. ICC thread covert channel exploits the side effects of multi-throttling thread. So in these side effects, executing an instruction with high computational intensity results in a throttling period proportional to the difference in voltage required of the currently and the previously executed instructions, as illustrated here. So the thread executes scalar instructions with IPC of 2, and inst0 loop starts executing with IPC of 1. Inst0 start in inst0 loop is throttled while ramping up the voltage VCC. Once the target VCC reaches the throttling is stopped. Reach the voltage, the throttling is stopped basically. And when the 512 heavy loop is executed, it's first throttled with while ramping up the voltage to accommodate for the 512 heavy loop. T0 throttling period depends on the computational intensity of the N0 loop, and the remaining voltage required for executing 512 heavy instruction depends on the previous VCC level that was reached when N0 was executed. And the second covered basically ICC covered channel. ICC thread cover exploits the multi-throttling thread side effect to build a covered channel between sender and receiver. So the sender executes a PHI loop with the computational intensity level between level 1 and level 4, and depending on the value of the those secret bits it wants to send. And the receiver can infer the 2 bits sent by the sender based on the measured TP throttling period of the 512 heavy loop. So the higher the power required for the PHI loop executed by the sender, the shorter the TP experienced by the receiver. Okay, so the second covered channel is ICC SMT covered, established across co-located SMT threads. So ICC SMT covered channel exploit the side effect of multi-throttling SMT, and in this side effect, when a thread is throttled due to executing PHIs, the co-located SMT thread is also throttled. So we actually we discovered that the co-located hardware threads are throttled together because the throttling mechanism in the core pipeline blocks the front end to the back end interface due to basically during 3 quarters of the time for both threads in the SMT core. So as illustrated here, so at the beginning, the threads execute scalar instructions with IPC of 2, and T0 start executing N0 with IPC of 1, and the T1 start executing 64-bit loop with the IPC of 1. T0 and T1 loops are throttled with while ramping the voltage VCC. Once the target voltage is reached, throttling is stopped. So T1 throttling period depends on the computational intensity of N0 executed by T0, which determines VCC level to which the processor needs to increase the supply voltage. So actually, ICC SMT covered exploit the multi-throttling SMT side effect to build a covered channel between sender and receiver. The sender executes a PHI loop with the computational intensity level, depending on the value of 2 secret bits it wants to send. And the receiver can infer the 2 bits sent by the sender based on the measured TP of the 64-bit loop. So the higher the power required by the PHI loop executed by the sender, the higher the TP experienced by the receiver will be. Okay, now the final covered channel, which is actually the thread covered, the ICC cores cover. So ICC cores covered exploits the side effect of multi-throttling cores. In this side effect, when 2 cores execute PHIs at similar times, the throttling period are exacerbated proportionally to the computational intensity of the PHI executed in each core. So this increase in the throttling period is basically due to the power management unit, which is waiting for the voltage transition of core A to complete before starting the voltage transition for core B. So as illustrated here, so T0 and T1 started execute T0 and T1 and core 0 and core 1 start executing in 0 and 128-bit heavy loop, both with the IPC of 1, and T0 and T1 loops are throttled. So once T0 target VCC is reached, T0 throttling is stopped. T0 continue to be throttled since basically the PMU will not handle a T1 voltage transition until T0 voltage target is reached. So T1 throttling period depends on the computational intensity of N0, which determines the VCC level to which the PMU needs to increase the supply voltage before handling T1 voltage transition. So ICC cores covert exploits multi-throttling cores side effects to build a covert channel between sender and receiver. The sender executes a PHI loop with a computational intensity level depending on the value of the 2 secret bits that it wants to send. And the receiver can infer the 2 bits sent by the sender because of based on the measured throttling period of the 128 heavy loop. The higher the power required by the PHI loop executed by the sender, the higher the TP experienced by the receiver will be. So I will next present our evaluation of I channels. So first, I will present our methodology. We evaluate I channels on Coffee Lake and the Cano Lake processors. We tested ICC covers and ICC cores, ICC threads covered and ICC cores covered on both processors, but we tested ICC SMT covered only on Cano Lake, as Coffee Lake it does not have or does not support SMT. So our main workload are proof of concept code of each of the 3 cover channels. And we compare I channels to 4 recent work that exploit different power management mechanisms of modern processors to build cover channels. Okay, so basically we compare ICC covered against NetSpectre, the state-of-the-art work that exploits the variable latency of PHIs to create a cover channel between two execution contexts running on the same hardware thread. The NetSpectre cover channels can send 1 bit per transaction, while our ICC thread cover channel can send 2 bits per transaction. And we compare ICC SMT covered and ICC cores covered against the DVFS covered and Turbo CC and PowerT. These are the state-of-the-art works that exploit different power management mechanisms of modern processor to build cover channel across core and SMT threads. So ICC SMT covered and ICC cores covered throughput is 145 times and 47 times and 24 times the throughput of DFS covered, Turbo CC and PowerT respectively. The 3 works exploit slow mechanisms compared to the current management side effects that our I channels exploit. So we have more results in the paper. For example, we have a fast per core. Okay, so we propose practical hardware and software techniques for mitigation of cover channels, of I channels. One of the solutions was fast per core voltage regulators. Other one is improved core throttling. And the last one is the secure mode of operation. So each one of the table shows that the effectiveness of and the overhead of each one of the proposed techniques. So let me quickly conclude my talk. So current management mechanisms throttle instruction execution and adjust voltage and frequency to accommodate power-hungry instructions. These mechanisms may compromise a system confidentiality guarantees. So our goal is to understand the throttling side effects of current management mechanisms and build high-capacity covert channels between otherwise isolated execution contexts. And finally, practically and effectively mitigate each of the covert channels. Variable execution time and frequency change due to running PHIs where it was characterized. So we observe 5 different levels of throttling in real systems. So we proposed I channels, new covert channels that exploit side effects of current management mechanisms to on the same hardware thread and across SMT threads and across physical cores. On 3 generations of Intel processors, I channels provide channel capacity 2 times that of PHI's variable latency covert channels, and 24 times that of power management-based covert channels. So thanks you for your attention. So this was the last work that we have. And do you have any questions on this work before I jump to the conclusion parts?
I don't see any questions on YouTube, but I think we have some other questions. So meanwhile, I'm asking my question, maybe others can also put their questions on YouTube that we can ask. So I have just a simple one actually here. So the core channels in I channels rely on the some certain system behavior characteristics while executing power-hungry instructions, right? And obviously this requires some time, and you already provided some results about throughput and stuff. But I was curious if it is enough to just like execute a few power-hungry instructions to observe this state change, and like how few instructions can we, power-hungry instructions can we execute to cause this difference in the system state basically. So can we change the state in a few nanoseconds, or is it supposed to be in microsecond order? Could you provide some more insights into this?
Yeah, there is like again, there is more details on the paper on this, but like I will give you more details on that. Basically, executing few instructions, about 10 instructions, which can be executed in few nanoseconds, can result this throttling effect. So it seems that there is a threshold in these processors that above it, for example, if there is a rare execution of power-hungry instructions, so then this mechanism will not be activated. So the threshold that we observed in the systems was like few instructions, let's say around 10 instructions, and this will start the throttling effect of the PHIs, which will result in this slowdown that we see in the system.
To me, just 10 instructions seem quite practical. Do you agree with that? So if we just like have not say, let's say Sander, but we have some benign application running, and it would be very often to see like more than 10 power-hungry instructions coming in a short amount of time, right?
Yeah, right. Like it depends on the application that's running. Like most or let's say many of the applications today are not using AVX. By the way, this is the reason that this mechanism exists. Otherwise, like if you know, like if these instructions are existing everywhere in every software, so there is no need to do this transition. These mechanisms basically exist in order to reduce the overhead or to increase the efficiency of code that does not using AVX. So code that is using scalars will not have the penalty, the additional voltage due to this high current instructions. So this is why this mechanism exists, because most, or let's say typical workloads does not involve high PHIs, like power hungry instructions. So in typical applications, like you will not see that. So if an attacker wants to send let's say we have two programs as we described in this paper, so he can easily do a communication between one thread and the other using this mechanism.
Okay, yeah, that sounds great. Thank you very much for answering.
Yeah, welcome.
Do we have other questions in the audience?
Maybe I'll piggyback on Girai's question while others are preparing questions. Jawad, this is very interesting work. Thanks. Actually, it's quite fascinating, I think, to have covert channels driven by these power management mechanisms. I think it's interesting to have covert channels, but piggybacking on Girai's question, maybe there are some benign applications that lead to quality of service and performance problems because they keep executing these power hungry instructions and switching between power hungry and non-power hungry instructions once in a while, right? So there are aspects of this work that are not necessarily quantified in the paper, but it could also be important. Maybe, for example, in a cloud environment, right? For example, if an application gets scheduled together with such a, let's say, application that switches between power hungry and non-power hungry instructions, overall system performance and quality of service provided to co-executing applications can degrade significantly.
Yeah, right. I agree with you. Like one of the aspects that we didn't study in our paper is as you mentioned, like the not covert channel, like side effect or side channel attacks. So basically, if an application is running in parallel to other application, let's say in the server, as you mentioned, so this application, this spy application can infer what's the other application that the victim application is running. So it can infer that it's running now AVX instructions and which level of AVX. Is it AVX1, AVX2, AVX 512? So it can infer data on that program. And if you assume that, for example, the attacker knows the stage of some algorithm that's running in that target or victim application, that it can infer also what that application is doing and at which stage is that application is running. So yes, like this part we didn't study, and maybe like follow-up studies can do that.
Yeah, so there could be multiple different types of issues, like the ones that you showed over here and the ones that you mentioned, and also certainly performance and quality of service and denial of service type of issues.
Yeah, right, definitely.
I have one more question. Can you go back to the solution or mitigation mechanisms that you mentioned? You didn't talk about them that much, but I think they're important to prevent this sort of issues. And maybe you can go into a little bit more detail into, because it seems like there's no perfect solution, right? they all come with overheads, or they all come with deficiencies, let's say.
Yeah, right. So like one of the solution, like we propose 3 mitigations, but one of them, like the first one is the per core voltage regulator. The target systems or the study system in our work basically are using a shared voltage regulator. So one of the solutions is to mitigate like the ICC cores covered, for example, which is exploiting the effect of due to the PMU is waiting for one core voltage transition to finish in order to start the other one. Like we can use a per core voltage regulator. So as we can see, this solution does not like it has a partial effect on the other 2 covered channels. It solves this covered channel, but it does not. It's partially. We mean here partially because like it makes the attacks more these attacks more like difficult because it shortened the throttling time. So instead, for example, of 10 microseconds, it can be let's say less than 5 microseconds of throttling time, and it has an overhead, as you can see, like it has the overhead on the chip area of between 11 and 13%. And additional one is the improving throttling. So here we mean like the ICC thread covered basically is utilizing that the ICC SMT covered, utilizing that once one of the thread is throttled, then both of the SMT threads are throttled. So in order to solve this, like the core can just throttle the thread that is running the PHI instead of throttling both of the threads, which eliminates this like side effect or covered channel. But the other ones are not solved. And the final solution is basically secure mode. This mode is disabling basically the feature that just raising the voltage for all of the workloads. Once once you are running let's say a sensitive code, so just ramp up the voltage for all of for the worst case. This for sure like have implications between 4 and 11% in additional power, and it will also affect the performance in some cases because as we know in these systems, like once you are running in the highest voltage, so then the frequency is dropped. For example, AVX 512 frequency is much lower than the highest frequencies that you can observe with scalar instructions. Yes, so this is regarding the mitigations.
Okay, great. Yeah, I think it's maybe there's more room for improving or evaluating these mitigations also going into the future.
Yeah, right.
Yeah, future work can address that.
Yes, exactly. Yeah. So we just like in high level propose this solution, but as you mentioned, like a deep understanding of these mitigations, and maybe proposing some more efficient and more effective mitigations. It could be a general like direction for future research in this area. Right.
Yeah. Okay, thanks. I don't have any other questions, but maybe others do.
I have a short question. So almost all my questions were already answered. So I have one additional short one. And is that, so your work studies I channels in interprocessors, but are these core channels also a problem in microarchitectures other than Intel?
Yeah, definitely. Like we, like we didn't fully characterize these effects on other architectures, but basically some of the throttling effects, for example, reducing the frequency once running PHIs, it can be observed also in other processors like AMD processors, and there is a public data on that without doing the experiments to the end. So these effects can be also exploited, but we didn't did a full characterization for these systems, but we suspect that these effects exist there because actually this is about physics. Like it should behave the same in all of these systems. The mitigation, or I mean the throttling effects or the throttling mechanisms can vary. For example, once one of the cores executing PHIs, the other core on the SMT thread does not have to be throttled. So some of these effects can be mitigated in some architectures, but regarding the throttling effect, it should be in all processors. So I know, for example, AMD processors are doing a different strategy than Intel. They are doing some mechanism that, for example, dynamically detects the with analog detectors the voltage drop, and they compensate or widening the clock frequency, or reducing the clock frequency dynamically, and mitigating this issue, but for a short time. And but for the long term, I mean for a longer throttling, they at the end they reduce the frequency.
It makes sense.
Mm-hmm. Okay, any other questions?
Yeah, maybe that's also an area of future work, right? Seeing whether these side channels, covert channels, exist in, or at what degree do they exist in other types of processors, and what can be done about it. I think that's a good direction. I think it's in general this is a trade-off between security and power consumption, right? Energy consumption. You can get rid of all of these by maximizing energy potentially, right?
Right. Exactly.
Providing isolation, but that's not what we want also.
Right. Yes, exactly. Like we want to apply the mechanisms once we need them, and try to gain the performance in cases that we less care about security. Yeah, because this is the trade-offs that we will see. But in general, these we didn't explore all of the power management mechanisms. So as you know, power management mechanisms are many exist. Many such mechanisms exist in recent processors, and maybe other mechanisms can also have security vulnerabilities that we didn't see. So this area in general is exciting to see what other parts can be exploited to do additional attacks. Either it's side channel attacks or covert channels in modern processors.
Yeah, I agree. I think there could be many other potential vulnerabilities in different power management and current management mechanisms. It'd be good to have a single solution that fixes all of them, right? But that may not be easy also, easy or efficient, let's say. Right. It may be easy, but it may be extremely inefficient, right?
Exactly. Yes. Yeah. Yes. Correct.
Okay, thanks, Jawad.
Thank you. Yeah, so these basically the papers that we covered in today's talk. So we have 4 papers. Again, like the papers were presented in HPCA, in ISCA, other one in Micro, and last one in last ISCA. So please read the papers. If you have any questions, you can ask one of the authors directly on that, and we will be happy to answer your questions. So actually, to conclude, so in this seminar, we provided a detailed overview of the state-of-the-art power management mechanisms, power delivery, and the security vulnerabilities of power management mechanisms in modern processors. So we conclude that power management, power delivery, and resulting security implications are critical and exciting areas to research to make modern systems both more energy efficient and high performance. So thank you for your attention. If you have any questions, again, last questions, please, I will be happy to answer.
Yeah, thank you, Jawad, for the detailed discussion on 4 papers. Of course, it took some time to cover all of these, but yeah, hopefully it was useful for people. And I agree with your conclusions. I think there's a lot more to research in these areas, especially as we discussed in the intersection of energy and security problems, as well as mitigations to all of these problems. And I should also mention to people who are listening that Jawad has another paper coming up at Micro on another energy efficiency mechanism called BurstLink. And maybe he'll give another Safari seminar about that later on when the paper is fully published.
Yeah, sure. Yeah. So we'll continue these seminars. I think it's very interesting to discuss this paper in this area. Like it's very close to my heart, this area, and I would like to see more people researching this area, and I will be happy to collaborate with researchers on this area.
Okay, sounds great. I don't see any more questions online, and I don't have any questions myself. Are there any questions from people who are participating on Zoom? Okay, if no questions, then I think people can certainly email Jawad with any questions they may have, and probably they will see him in future seminars also. Okay, thanks a lot, Jawad.
Thank you, Onur. Thank you all.
Okay, take care.
Thank you. Bye-bye.